Hey everyone, it's Kendall from the Recording Lounge podcast, and today I want to talk about 7 audio equations you actually need to know. Behind a lot of what we do, there's actually a lot of math involved, especially in the world of acoustics or in electronics. But for the most part, let's be honest, we don't really need to know most of it. I mean, it certainly doesn't hurt anything, but most of it will never come up in a session or help us solve a real-world problem. However, I do think there are a few essential equations that every audio engineer needs to know. I'm going to talk about 7 of them, or at least 7 types of equations, and even if you don't consider yourself to be a math person, I think you'll find today's episode interesting. For each of these equations, I'm going to give you the basics, I'll give you some examples, and I'll throw in a little bonus stuff for the super nerds like me and anyone out there who wants to learn a little bit more. So let's get started. Okay, so some of the most basic math and most important math you need to know, and possibly already know, involves frequencies and notes. We've likely all seen tuners with the little indicator that says A equals 440, and as most of us probably know, that means 440 hertz. The most basic thing to understand here is the relationship of frequencies and octaves. When we go up an octave, we double that to 880 hertz. If we go down an octave, we halve it to 220 hertz. An open A string on a standard tuned electric guitar is 110 hertz as a fundamental, and the low A on a bass guitar is 55 hertz as its fundamental. It's all a doubling and halving. On the standard musical octave range of 8 octaves, 440 hertz is also known as A4, or A above middle C. But beyond that, what about the other notes? How do we get there? Well, this all has to do with a constant developed for a 12-tone tuning system, and that constant is 2 to the 1/12, which is about 1.05946. Let's call this K for now. So to go from a perfect 440A down a half step to A flat, we would do 440 divided by K, our constant, which gives us 415 hertz. To go up from A half step to B flat, we do 440 times K, which gives us about 466 hertz. So to continue on our graph left or right, if we're charting this all out, we would just continue multiplying or dividing by K to go up or down in half steps. And again, K is 2 to the 1/12. So again, if we're at A 440 and we want to go up to a B flat, we'd multiply by K, giving us 466 hertz. If we want to go up to a B, another half step, we'd multiply 466 times K, which gives us 493.9 hertz. So for every octave up, we multiply by 2. For every octave down, we divide by 2. For every half step up, we multiply by K. For every half step down, we divide by K. With these 2 basic formulas, we can fill out an entire chart for every note in every octave. Knowing this also makes it easy to calculate the same thing for a different pitch standard. So for example, if you were tuned to A equals 443, it works exactly the same. Start with your A4 frequency, which is going to be 443. You can find the octaves by halving or doubling. You can figure out the half steps up or down by multiplying or dividing by K. And you can fill out the chart from there. Now, if you don't want to fill out your own chart, stick around to the end of the episode and I'll tell you how you can get an Excel workbook with all of these equations in them made by yours truly. Our next equation, or set of equations, is kind of a 3-in-1. It's the relationship between wavelength, room modes, and the harmonic series. So let's get into it. Calculating wavelength is actually quite easy. You just take the speed of sound, let's say 1,130 feet per second, divided by your frequency, let's say 500 hertz. And that gives us 2.26 feet. That's the wavelength of 500 hertz. Higher frequencies have shorter wavelengths and lower frequencies have longer wavelengths. This equation works in reverse too, so if you wanted to figure out the frequency of a 12-foot wave, you would just do 1,130 divided by 12, and that gives us 94.1 hertz. Now, we use the same basic idea when calculating room modes. However, when we apply this concept to room acoustics, many people forget that the first room mode, we have to measure it as a full path from wall to wall. So we actually have this equation. So instead of speed of sound divided by length, we use speed of sound divided by 2 divided by length. That's our first room mode. So in a room that's 19 feet long, that gives you 1,130 divided by 2 divided by 19, which equals 29.7 hertz. That is our first room mode. Now, a room mode is just a resonance. That's really all it is. It's a repeatable, predictable resonance based on the dimension in a room. And our room will have resonances at this first mode and all of its multiples. This follows the harmonic series. So let's round this up to 30 hertz just for simple demonstration. In our 19-foot-ish long room, we'll have resonances at 30, 60, 90, 120, 150, 180, 210. It's just frequency times 1, 2, 3, 4, 5, 6, all the way up to infinity. The width dimension and the height dimension also have resonances that work this exact same way. Now, this is arguably the most fundamental equation for room acoustics, and something that acousticians and studio designers spend a lot of time playing with. The way these different dimensions and modes interact creates the sound of your room, and ultimately it will decide how linear your room is or how accurate it can be. For example, you've probably heard from me or other acoustics nerds that you should avoid a cube room at all costs, right? But do you really know why? If you have a room that's 10 by 10 by 10, you're going to have strong resonances at 56.5 hertz and 113 hertz, but no modal support below or in between. And that's a huge problem. The goal in designing a room is to have even modal spacing with minimal overlaps and minimal gaps. For example, a room that is 14 by 19 by 23 will have modal support at 25, 30, 40, 50, 60, 73, 80, 90, and 98 hertz with no overlaps until about the 120 hertz region. So we would say this room has good modal spacing or modal distribution. The better we can get this spacing and distribution and to a higher frequency, the easier it will be to treat, and it will be infinitely more accurate than the 10 by 10 by 10 room. This is basically a simple mathematical proof of why I'm always talking about room acoustics, and why some people might find it harsh of me to say, don't even bother trying to record or mix in a room that's 10 by 10 by 10. That's not necessarily even my opinion, it's provable by math. You'll never really have an accurate room that's 10 by 10 by 10. It can't happen. The amount of treatment needed to eliminate those issues caused by the wide-spaced modes and the overlapping that exists, you'd basically have to make the room anechoic, and there'd be so much treatment in the room, you probably couldn't enter it. So I'm trying to help you out, right? Like, I'm trying to be honest with you where we live in a time where there's so much misinformation about acoustics and things like that on the internet, and I'm trying to help you, right? You'd be better off working on headphones or finding a different room, because trying to spend all this money trying to treat that cube room, it's just not going to work as well as you think. Now, one final note about this. I mentioned that room modes follow the harmonic series, meaning they follow the formula of frequency times 1, 2, 3, 4, 5, all the way up, right? Well, interestingly, this is also exactly how saturation plugins work, and honestly, how most instruments work. But for example, if you send a 100 hertz wave into a saturation device of some kind, you'll likely get harmonics at 200, 300, 400, etc., all the way up to infinity. Now, the exact distribution and loudness of each of these harmonics completely depends on the type of saturation device. For example, if the device says it has a lot of even order harmonics, that's going to be the even multiples of our fundamental frequency, so multiples of 2x, 4x, 6x, and so on. So in our 100 hertz example, that would be 200, 400, 600, etc. While the odd order harmonics are going to be 3x, 5x, 7x, and so on. So with our 100 hertz example, we'd have 300, 500, 700 hertz, etc. Now, I want to clarify, there's nothing inherently bad about even order harmonics or odd harmonics. In fact, most devices have some combination of both. Rarely is a distortion or saturation device solely even order harmonics or solely odd order harmonics. It's more about the relationship between them, which, as you can imagine, could be combined in an infinite number of ways and will change the wave shape and the frequency makeup of what you send into it. And that's why these devices sound different. Okay, another important equation that every audio engineer and producer should know is how to calculate milliseconds from a BPM. For example, if you're at 120 BPM and you need to set a dotted eighth note delay, how do you do that? Well, many people know that the basic equation is 60,000 divided by BPM equals a quarter note in milliseconds. So at 120 BPM, your quarter note is 500 milliseconds. To get an eighth note, you would divide that by 2, which gives you 250. Divide it by 2 again, and you get a 16th note at 125 milliseconds, and so on. If you need to make a dotted note, which basically is a value of 1.5 times the note, you would multiply by, guess what? 1.5. So for example, if our eighth note is 250 milliseconds, you multiply that by 1.5, that gives us 375 for a dotted eighth note. Now, for triplets, a lot of people mistakenly divide a quarter note by 3, and they think that that is a quarter note triplet. But that's a mistake, and if you're not used to reading music notation, then you probably wouldn't catch it. So technically, when you divide a single quarter note into 3 beats, we write that as 3/8 notes. So a quarter note triplet is actually 2/3 the value of your quarter note. And when you divide a quarter note by 3, you get an eighth note triplet value. So you could take your quarter note value, let's say at 120 BPM, 500 millisecond quarter note, and you could multiply it by 0.6666 repeating, and that would give us about 333 milliseconds. But again, that's a quarter note triplet. Most of the time when people are talking about triplets, they're thinking about ba 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 ba, right? You're dividing one beat into 3, and that would give us an eighth note triplet, which would be 166 milliseconds, which is 1/3 of 500 milliseconds. Now, something else that might trip up someone who's not used to reading musical notation might be the difference in a whole note length versus a measure length. Some people erroneously assume that one measure equals one whole note, but that's not correct. Regardless of time signature, a whole note is still 4 quarter notes. So, for example, if you are in 5/4 time, which means there are 5 quarter notes in a measure, then to fill up an entire measure, you would use a whole note and a quarter note together. That would give you 5 beats total. So how does that translate to our equation? Well, the easiest way to figure out the length of a measure is to multiply your whole note value by the time signature as a fraction. So for example, if you're in 5/4 time at 120 beats per minute, your whole note value is 4 quarter notes that are 500 milliseconds each, so 2,000 milliseconds for a whole note. If you multiply that by 5/4, which is 1.25, you get 2,500 milliseconds, and that is the length of a measure of 5/4 at 120 beats per minute. Now, to complicate things further, some music writers will use a whole rest to denote resting for a whole bar, but technically that's incorrect. A whole rest is still just resting for 4 beats. So to denote a measure of silence in 5/4 time, you should write a whole rest and a quarter rest, which is 5 total beats of rest. But some people just write a whole rest for resting for an entire bar, and that's just kind of lazy. But anyway, now you know. Now, the next equation you might know or you might have heard, but you may not realize why it is the way that it is. I'm talking about the 6 dB rule of decibels. Or is it the 3 dB rule? Or the 10 dB rule? Well, in fact, it's all of them. It just depends on the context. So, as a general rule, because sound pressure is on a logarithmic scale, for every doubling of sound pressure, we get an increase of about 6 dB. So on paper, 106 dB is, quote, twice as loud as 100 dB. And 70 dB is, quote, half as loud as 76 dB. Now, this rule also applies to distance. So if we're 100 feet away from a sound system and they're playing music at 100 dB, moving to half the distance, so we're now 50 feet closer, that would be twice as loud, meaning 106 dB. If we halved our distance again and went to 25 feet, that would get another 6 dB louder, so 112. We are twice as close, meaning it is now twice as loud. The same is true for mic placement. Moving a mic from 3 inches to 6 inches would get about 6 dB quieter, and moving it from 6 inches to 1 foot would also get another 6 dB quieter. Now, this is one of the reasons why it's so important for live vocalists to stay right up on the mic at all times. When you're that close to a microphone, a small distance can make a big difference. Moving from ½ inch to 1 inch away, you will lose 6 dB. Frankly, this is also why I think the technique of, quote, working the mic is a bit overstated and dramatically performed. You don't really need to move that much to reduce your volume for loud notes. For example, if you move from ½ inch to 4 inches, you'll lose 18 dB. In my opinion, most singers should never have to work the mic any more than this. So what's the equation that proves all of this? Well, no surprise, it's a log equation. When dealing with sound pressure, most of the time we're going to be doing a logarithmic equation. And that sounds scary, but it's really not. For example, in this case, we would use 20 times log A over B, where A is the original distance and B is the new distance. That answer will give us a change in decibels. So let's go back to our example where we're standing 100 feet away from a PA that's producing sound at 100 dB SPL, and then we move to 50 feet. So for that equation, we would do 20 times log, and then in the parentheses, 100 over 50, which gives us 6.02 dB. So technically, the 6 dB rule is 6.02 dB. That's also why the max dB reading on your DAW is often 6.02 rather than a perfect 6.0. But we can calculate this for any distance, and it gives us the proper sign as well, which is really cool. So let's go back and say we're 100 feet away from 100 dB SPL sound. And let's say we wanted to get away from the PA so that we could have a conversation with our friend. So we moved to 500 feet away. So how much quieter would that be? So for this, we would do 20 times log, and then in the parentheses of our logarithm, we do 100 over 500. Again, original distance over new distance. And that would give us minus 13.9. So it's about 14 dB quieter when you move to 500 feet. The 20 times log formula is also used when adding coincident sound sources. So, for example, say you take a track in your DAW and you duplicate it. Just intuitively, you would probably guess, well, now it's twice as loud. And you're right. If you do 20 times the log of 2, you get 6.02 dB. What if you duplicated it 50 times? How much louder would it be then? Well, conveniently, if you're working with coincident sounds, meaning identical sounds, you can do 20 times log of 50, and that gives us 33.98. So 50 duplicates of the same sound would be 33.98 dB louder than the original. You can test this out for yourself. You can take any wave file with a relatively consistent volume, something like a distorted guitar, and turn the level down to, let's say, minus 40. Hard pan it to the left so you're not getting affected by the pan law of your DAW, and then duplicate it 50 times. Your master bus should read somewhere around minus 6.03. Okay, so what about the 3 dB rule? Where does that come into play? Well, the 3 dB rule comes into play for 2 primary scenarios. One, when we're dealing with incoherent sound sources, so non-identical, and 2, when we're dealing with power. So just like we talked about how duplicating a track will give us an increase in 6.02 dB, well, that's just it. It's a duplicate of our original, meaning it is perfectly coherent in every way. It's identical in phase and frequency and volume and everything. That means it's a perfectly coherent signal. But what if we have 2 guitar tracks from guitar player 1 and guitar player 2, and they're playing back at the exact same level, but they're not coherent. They're a different performance, different phase, different frequency. They're 2 separate takes. Well, in that case, we're dealing with incoherent sound sources, and we would only see an increase of about 3 dB. And in these cases, we don't use the 20 times log formula, we use 10 times log. So say we have a distorted guitar and we're playing it back around minus 12 dBFS, and we record a double of it and we pan it to the other side, also around negative 12 dBFS in level. And we're trying to figure out, well, how much louder is it going to get now? It's not still going to be negative 12. They're going to add some way. Well, for that, we would do 10 times the log of 2, which gives us 3.01 dB. If we recorded 4 more guitar tracks, all playing back about the same level, about minus 12, we could estimate how much louder all 6 tracks would be by doing 10 times the log of 6. That gives us 7.8 dB. So your individual tracks all playing back at minus 12 would now show about minus 4.2 on your master bus if they're all playing at the same time. You could also use this formula to estimate how much headroom you're going to need on your master bus because of the volumes of your tracks. For example, let's say somebody sends you a huge session with 150 tracks, and let's say you gain stage them to roughly minus 18 on average. How much louder are they going to be when they're all playing back at the same time? So assuming there are no duplicate tracks and we're dealing with just individual incoherent sound sources, you could do 10 times the log of 150, which gets you 21.7 dB. Now, all of your tracks are playing back at minus 18, so your master bus would be clipping in this instance, right? We've added 21.7 dB. So from your original minus 18 reference, you'd be hitting about plus 3.75 now. But if you grabbed all of your faders and you brought them down to minus 10, so now technically your reference is minus 28 for all of these tracks, you'd have plenty of headroom, and your master bus would now only be hitting about minus 6. Now, I mentioned that the 3 dB rule also applies to power. What I mean is, anytime we're dealing with wattage, for example, or speaker sensitivity, we use the 3 dB rule instead of 6. So a 100-watt guitar amp is only about 3 dB louder than a 50-watt guitar amp, which is only about 3 dB louder than a 25-watt guitar amp. That's why if you've ever had a guitar amp with one of those half-power switches, the effect of it is pretty subtle. It doesn't actually reduce your volume that much, only by about 3 dB. Now again, in the room, we are hearing the sound as sound pressure. So if we want our amp to be half the volume, we need to reduce it by 6 dB. So if you wanted to reduce the volume of your 100-watt amp by 6 dB, you would need to quarter the power. You'd need to go down to 25 watts. However, this also applies to speakers. So if you have a speaker with a 100 dB sensitivity rating and you go from a 112 cabinet to a 212 cabinet with 2 identical speakers, you'll get a 3 dB bump in output. Similarly, going from a 212 cabinet to a 412 cabinet would get you another 3 dB increase. The signal doesn't lose volume by splitting to multiple speakers because it's incredibly low impedance, 4 ohms, 8 ohms, etc. So you're effectively getting free volume by using a cabinet with more speakers. So in theory, a 25-watt amp with a 212 cabinet will be just as loud as a 50-watt amp with a 112 cabinet. Now, there's a few other useful variations of these formulas that I wanted to talk about. Let's say you needed to calculate exact dB values rather than just how much something will increase or decrease. Again, we need to use the 10 times log formula for incoherent sounds and 20 times log for coherent sounds. But the formula within the logarithm is slightly different. So for example, say we had 3 vocalists and one is singing at 77 dB, one is singing at 79 dB, and the third is singing at 82 dB. How loud would the total SPL be? Well, these are incoherent sound sources, meaning they're not the same person, they're not singing exactly in time, they have different tone of voice, right? So the formula we would use is 10 times log, and then in our parentheses, we'd go 10 to the SPL 1 over 10, plus 10 to the SPL 2 over 10, plus 10 to the SPL 3 over 10, and so on, all the way for as many sound sources as we have. So in this case, with 77 dB, 79 dB, and 82 dB, that would simplify to 10 times log, and then in our parentheses, 10 to the 7.7, plus 10 to the 7.9, plus 10 to the 8.2, right? That's our SPL divided by 10 as our exponent. And if you simplify that, that gives us 84.59 dB. If instead we were doing coherent sound sources and we're in our DAW and we're duplicating tracks, but we have 3 different volumes for those tracks. So let's say we created 3 duplicates of a track and one is at -6, one is at -12, and one is at -13. How loud would it be on your master bus? Again, this is for a coherent sound source, an identical sound source effectively. For this, we need to use the 20 log formula because the sources are coherent, but there's a slight change in the formula. So we would do 20 times log and then in our parentheses, 10 to the SPL1 over 20 plus 10 to the SPL2 over 20 plus 10 to the SPL3 over 20 and so on and so forth. So for this, you could simplify that to 20 times log of 10 to the -6 over 20 plus 10 to the -12 over 20 plus 10 to the -13 over 20. And if you simplify that, it gives us -0.21 dB. And again, you can test this in your DAW. Set up 3 duplicates of a track, one at -6, one at -12, and one at -13. Pan them to one side. Again, you're trying to remove the effect of your pan law, which is going to reduce your center pan sounds by 3 dB or 4.5 or 6 dB, depending on how you have your pan law set. But pan them hard left, and your master bus should read -0.21. So what about the 10 dB rule? Where does that come from? Well, the 10 dB rule is more of a subjective measurement of loudness. There have been many, many studies on this over the years, and even though the math says that 6.02 dB is equal to a doubling and -6.02 is equal to halving, many studies have shown that human beings consistently perceive 10 dB as being a double or a half. Now, some have argued this is because of the effects of room acoustics and reflections complicating the 6 dB rule. Some have argued it's just how our brain hears and the frequency response of our ears and how bad human hearing is. But regardless, it's a subjective measurement. If you polled 10,000 people and asked them to turn up a volume control until it's twice as loud as it was originally, you'd get a lot of answers, anything from a few dB up to maybe 20 dB. Much of it depends on the starting volume as well, because our perception of dynamics is also nonlinear. We tend to have better distinction of dynamics at lower volumes and worse at high volumes. So, for example, if someone set a piece of music at 60 dB SPL and your proctor says, okay, turn up the volume control until it reaches twice as loud as it was before, somebody might stop it at 65 dB. But if you started that initial music at 100 dB, then for them to keep turning it up, they might not say stop until 112 dB. So take from this what you will. There are not really any great equations for it because it's a subjective measurement. It's an average based on thousands of controlled experiments. And to my knowledge, it's not really provable with any math, at least not yet. So to summarize, we use the 6 dB rule most often, particularly when referring to sound pressure or voltage changes. This is probably the most correct answer when somebody's talking about basic doubling or halving when it comes to distance or volume changes. We also use the 6 dB rule when we're talking about coherent sound sources. We use the 3 dB rule when we're talking about incoherent sound sources or when we're talking about sound power, wattage, or intensity. And we use the 10 dB rule if we're referring to a perceived loudness change. I know this one's a little bit more complicated, but again, if you're interested in a spreadsheet that has all of this already worked out in it, stick around to the end of the episode. Our next equation is something that I think many people have thought about, but in the moment, it's kind of an easy thing to get confused on. How do you convert samples to milliseconds? So unfortunately, because we use different sample rates, this can be a little bit confusing and there's not a great easy trick to remember. You just have to understand the basic formula. So the number of samples divided by sample rate in kilohertz equals our delay time in milliseconds. So for example, at 48 kilohertz, one sample is equal to 1 over 48, which equals 0.0208333 repeating milliseconds. Going the other way, from milliseconds to samples, you just do the inverse. So sample rate in kilohertz times milliseconds equals samples. So, for example, multiply 48 times 0.0208333 repeating, and you get 1. For another example, say we're at 192 kilohertz. We divide 1 over 192 to give us 0.0052 milliseconds per sample. So if we wanted to figure out the delay time of, say, 500 samples, we'd just do 500 over 192, which gives us 2.604 milliseconds. One rule of thumb that might be handy to remember is that for every doubling of our sample rate, the length of a sample halves. So if the length of a sample at 48 kilohertz is 0.0208, then at 96 kilohertz, this is 0.0104. In the days before automatic delay compensation and hardware insert delay calculations, you had to do this manually in your DAW, so you had to get pretty good at this math. I know this one's pretty easy and straightforward, but still, it's really important to know. Now, we just talked about samples versus milliseconds, but perhaps a more useful thing for most audio engineers is understanding the relationship of delay and distance. So if one sample at 48 kilohertz is 0.0208 milliseconds, okay, why does that really help me? Well, say you're trying to time align two microphones so that they have a better phase cohesion and less comb filtering problems. Some people will try to do this in the edit window by moving around the waveforms until they look visually lined up, but personally, I don't recommend this approach. In most DAWs, the smallest increment that you can move a waveform is one sample. And even though 0.0208 milliseconds seems like a tiny number, if you convert that into a distance, that's about a third of an inch. So that's not actually that fine of a resolution, but we'll come back to that here in a minute. For now, let's talk about how to convert between delay and distance. So first things first, you need to define your speed of sound. An easy number that many people use is 1,130 feet per second. We're going to talk a bit more about speed of sound here in a bit, but for easy numbers, let's just use 1130, right? So if sound travels 1,130 feet in 1 second, that means in 1 millisecond, it only travels 1.13 feet, right? So essentially, speed of sound over 1,000. Seems pretty simple, right? So to go from delay time to distance, just multiply the delay amount times 1.13 and you get your distance. So for example, let's say you see someone off in the distance and they slam a car door and you hear the sound 200 milliseconds later. You can multiply 200 times 1.13 and estimate that the car is 226 feet away from you. Now, here's another example. Let's say you clap your hands near a building and you hear an echo 200 milliseconds later. That doesn't mean the building is 226 feet away. In fact, it's likely half of that, 113 feet away. The delay time we're calculating is the total path of the sound, right? From the source, your hands clapping, to the building, and back to your ears. So the sound travels 113 feet from your hands to the building, it reflects and travels 113 feet back to you, and you hear it 200 milliseconds later. Now, let's go the other direction. This is probably one of the most relevant formulas of today's episode. Let's say we have one microphone right up on a guitar amp and a room mic 12 feet away. By how much will the room mic be delayed? To go this direction, we need to invert the formula to get our constant. Instead of doing speed of sound over 1,000, we need to do 1,000 over the speed of sound. So if we're using 1,130 feet per second as our speed of sound, we would do 1,000 over that, which gets us about 0.885. So to calculate the delay on our room mic 12 feet away, we just multiply 12 times 0.885, and that gets us about 10.6 milliseconds. This is a very important formula to know. It's important to know when time aligning mics or PA speakers, or even when trying to set the pre-delay on a reverb. For example, if you want it to sound like the walls are 50 feet away from your vocalist, you could assume a total path length of 100 feet, right? 50 feet to the wall and 50 feet back. That means a total time of 88.5 milliseconds before you actually hear the room sound. Now, remember when I said that moving around waveforms in your DAW edit window is not necessarily the best approach for time aligning things or getting phase relationships better? Well, here's why. Say we're trying to time align two close mics on an electric guitar amp. In our last equation, we talked about how one sample at 48 kilohertz was equal to 0.0208 milliseconds. Well, now we know that if you multiply the delay time by 1.13, it gives us a distance in feet. So 0.0208 times 1.13 equals 0.024, which is about 0.28 inches. And that's not really a fine resolution when trying to time align two microphones to have the tightest phase relationship possible. Now, sure, if you're recording at 96 kilohertz instead of 48 kilohertz, one sample would be half that length, so you'd be moving things around 0.14 inches per sample. But that's still as good as it can be. Instead, the better way to handle this is to use a plugin for precision time alignment, and my favorite one out there is Eventide Precision Time Align. On this plugin, you can move things around by microseconds, which is 1,000th of a millisecond. So if we use our formula, 0.001 milliseconds times 1.13, that gets us 0.0011 feet, or about 0.014 inches. So worded practically, that's 14 thousandths of an inch, which is roughly the thickness of an Evans G14 drum head. That is a much finer resolution that we can fine-tune phase relationships between two microphones. Now, one more interesting thing to note about this is that you can actually calculate the comb filtering based on a microphone movement of X inches or a shift of X samples. If you do this, you'll see that at 48 kilohertz, a shift of one sample will have its first comb filter null. This means a complete null canceling to silence at about 24,038 hertz, which is above the Nyquist limit of 48 kilohertz. So you wouldn't even hear it. Now, don't get too excited. You would start to get some amount of cancellation below 24 kilohertz, but you wouldn't actually get a full cancellation until then. I find you start to notice cancellations in phase about as low as a decade below your first null calculation. So that's a factor of 10, meaning if your first full null is at 10 kilohertz, then you'll actually be able to notice cancellations audibly as low as 1 kilohertz. So even a one sample shift can have a noticeable effect on your high mids. This again supports the argument of using something like Precision Time Align for shifting your waveforms around rather than your DAW's timeline. The super fine resolution really allows you to fine-tune this better than any manual edit can. Another big plus of Eventide Precision Time Align is that it shows you the distance in imperial and metric at the top, and it shows you the sample amount. So it makes it really handy. You don't even have to whip out the Excel spreadsheet. You can just look at the plugin. Now, for our last equation of the episode, you might find it funny that I've waited this long to talk about it, but it's only really because it's the most complex of all of them. And I'm talking about the speed of sound. Usually that's around 1,130 feet per second or 343 meters per second. But I bet that most audio engineers out there don't actually know how we get that number or where it comes from. In our last example, we used 1,130 feet per second, but is that really accurate? The speed of sound is complicated. It's affected by temperature and density and the elasticity of a medium. We have to use different equations for solids, liquids, and gases, and it's not something that's always intuitive. For example, within the realm of gases, the speed of sound increases with lower densities. This is why breathing in helium makes your voice sound higher. But if that's true, then why is the speed of sound in a solid so much faster? It's way more dense, right? Shouldn't it be the opposite? Well, that's because of something called Young's modulus, which is a ratio of stress versus strain in a material. Essentially, how easy is it to pull apart when force is applied lengthwise? So it's not so much that steel is denser than air, it's also that it's much, much harder to pull apart at a molecular level than air. This is why the speed of sound is so fast in solids. So to be more precise, 1,130 feet per second is the speed of sound in dry air at 72 degrees Fahrenheit. Now, in much of the scientific community, room temperature is sort of assumed to be 20 degrees C, which is about 68 degrees Fahrenheit, which actually makes a more accurate estimation of speed of sound in imperial to be 1,126 feet per second. Now, On the surface, really the only thing you need to know about how to calculate the speed of sound in air is the temperature. But in reality, you technically need to know the molar mass of the gas as well as the adiabatic index, and you need to use a constant that we refer to as R. So the true scientific equation for the speed of sound is the square root of YRT over M, where Y is the adiabatic index, which is about 1.4 for air. R is the constant 8.314 joules per mole times K. T is the temperature in Kelvin, and M is the molar mass of air, which is 0.02896 kilograms per mole. Now, you might be thinking like, holy cow, that's a lot of information, and when do I ever really need to know that? And I agree with you. You don't actually need to memorize that equation or all of those constants. What's important to note is the speed of sound will change with different air temperature, and quite a bit at that. Now, I've simplified this equation a little bit, and I've come up with one that gives us a pretty accurate estimate that doesn't require a bunch of crazy constants, and it is 1086.92 times the square root of 1 plus, in parentheses, the temperature in Celsius over 273. This equation accounts for the Kelvin to Celsius conversion, as well as the adiabatic index of air, the molar mass of air, and our constant R. For the types of temperatures that we encounter on Earth, this equation is accurate to about 0.2 feet per second. For extreme positive or negative temperatures, the margin of error increases, so this is still just an estimate. So let's use this simplified equation to estimate our speed of sound at room temperature, which would be in most studios, let's say 68 degrees Fahrenheit. First thing we need to do is convert Fahrenheit to Celsius, which means we subtract 32 and multiply by 5/9. So 68 minus 32, which gives us 36, times 5/9, which gives us 20 degrees C. So calculating the speed of sound then becomes 1086.92 times the square root of 1 plus 20 over 273. We're going to simplify 20 over 273 to 0.0732. We add that to 1. We take the square root of 1.0732. That gives us 1.03598. We multiply that by 1086.92, and we get 1126.03 feet per second. So why does this matter? Well, if you're in the studio world, chances are your studio is going to be around room temperature, so you could probably assume the speed of sound is relatively constant somewhere between 1,125 and 1,130 feet per second. But if you're a front of house engineer doing a summer tour and it's 95 degrees outside, the speed of sound is going to be much faster, closer to 1,154 feet per second. Now, that may not seem like a big deal, but suppose you're trying to calculate the delay time of your mains, which are 100 feet away from the booth. If you used 1,126 feet per second as the speed of sound, you'd get 88.8 milliseconds. But in reality, at 95 degrees, that's more like 86.6 milliseconds. So you're a full 2.2 milliseconds off. And if you're trying to time align your mains to delayed fills or delay your in-ear monitors to match the mains, your math would be off by enough to cause noticeable phasing and comb filtering. If we use a comb filter equation that I mentioned earlier, a 2.2 millisecond difference would cause a full cancellation as low as 227 hertz. That's not subtle, and it's not acceptable. So I think it's really important that audio engineers at the very least understand how drastically temperature will affect the speed of sound. And if you're outdoors, or even if you're indoors with a really high temperature, that will affect the sound of things, especially when it comes to time aligning things. Okay, so I know that was a lot. I know this episode was really geeky. And I'm not saying you need to memorize all of this stuff, right? I'm just saying it's important for you to know about it. I'm saying it's important for you to have a grasp of what it all means and why it can be important in certain situations. So if you're like me and you don't like memorizing equations, but you find them interesting, you can download my Excel spreadsheet that I made that has all of the equations I talked about in this episode. The main reason I made this episode is because I use this spreadsheet. And I thought, what if I did an episode about it? And what if I gave it to people who listen to this episode? So if you want the spreadsheet, all you have to do is head over to our Discord chat. I'm going to be posting it in the news and updates section on the left. To get to the Discord, just go to recordingloungepodcast.com, and right on the front page, you'll see a link to our Discord chat. I hope you'll consider getting involved there. It's a really cool community, a lot of cool people, a lot of smart people. And personally, I've really enjoyed it. It's a great way for me to keep up with everyone, considering that I'm the type of podcast that doesn't put out 3 episodes a week, right? I'm trying to set a new goal to put out 1 episode a month, just like I used to, as well as putting out some more YouTube content, maybe 1-2 videos a month as well. If you have any questions or podcast episode suggestions, please send them in the Discord or send me an email at recordingloungepodcast.com. And make sure to check out our YouTube channel, youtube.com/recordinglounge. If you have any ideas for YouTube videos, send those my way as well. I'll talk to you next time. See ya.